Welcome to Ask and Learn.
We want to produce a graph of f equal to x over x cubed plus x squared plus 1 that reveals all the important aspects of the curve, and in particular we want to use the graphs of f prime and f double prime to estimate the intervals where the function is increasing, decreasing, find any extreme values, intervals of concavity, and any possible inflection points. So I went ahead and found the first and second derivatives and went ahead and plotted those already and found all of our possible critical points. Just to save a little bit of time, because otherwise this video would take probably well over an hour to do by hand. And over on the left, this graph was just what happened when I plugged it into my calculator right away. So maybe this is a good curve of it. I mean, it looks pretty nice. But using what the information we'll get from the first and second derivative graphs, we may be able to see, oh, we needed to zoom out a little bit more. Or maybe there's an area of the graph we need to zoom in on. So let's just go ahead and get started by estimating our intervals of where the function is increasing and decreasing. So we know that a function will be increasing when f prime is strictly larger than 0. And so maybe I should give a little bit of rationale behind why I chose these windows for each of these graphs for f prime and f double prime, because I actually did choose these. So the first thing I did was I just zoomed super far out and made sure that I found all of my x-intercepts, because I don't want to lose any of those. So that's just pretty much how I went about choosing both of the intervals, just to make sure that all of our x-intercepts are there, because those will be important for us. And also something else, notice that around 1.5 or negative 1.5, it looks like we have a vertical asymptote that is happening, at least from the sketches of the graph. And if you zoom really far out, it looks like it's getting really close to negative 1.5 for that vertical asymptote. So I just went ahead and included that as well. It's not exactly that value, but it's somewhere around there, just estimating using the graph. All right, so now we know it's going to be increasing from negative infinity up until our vertical asymptote, which is going to be around negative 1.5. Then we're going to union this with, well, it looks like it's positive on the other side of our vertical asymptote, so negative 1.5. And it looks like it's positive until we hit our actual first x-intercept, 0.657. And then it approaches a horizontal asymptote at y is equal to 0, because you might notice that our denominator has a larger power than our numerator. So we know it should just keep on going to 0 as we get larger and larger for our x values. So this would be our interval of increase. Now let's go ahead and find where the function is decreasing. And so remember, that's going to be where f prime is strictly less than 0. And that only occurs on 0.657 to infinity. All right. Now, something we might need to do for a possible max or min is to look at any undefined values as well as just where the function is equal to 0 at. But since we have the same thing, or essentially the same thing in the denominator of our original function f as well as our derivative of f, we won't have to worry about that, because we'll know that whatever values are undefined for f will also be undefined for f prime. All right. Now you may notice over here at our 0 of f prime, well, it is increasing after it, or it's increasing into the point, and then it's decreasing after the point. So that tells us at x is equal to 0.657 that this should be a local max. Okay. And now we can go ahead and look for concavity and possible points of inflection. So just like before, we're going to have this vertical asymptote around negative 1.5. And here we actually do have a little bit more interesting values. All right, so concave up, remember, is going to be where an f double prime is strictly larger than 0. So again, our denominator should have a larger power than our numerator. So we know that there's this horizontal asymptote at y is equal to 0. And so that means we're going to go from negative infinity to our vertical asymptote at about negative 1.5. And then union this with, well, then we become positive again around negative 0.49 until 0, union, and then after 1.1 to infinity. Next for, not decreasing, this should be down. Oh, and I also said increasing there. This should actually be concave up, is what we found. So let me go ahead and write that. So this should be concave up and concave down. All right, so this is when f double prime is strictly less than 0. So we are negative for our second derivative graph to the right of our vertical asymptote. And this will go on until about 0.49. And we're going to union this with then 0 to 1.1. So now all we need to do is go to our critical values and check to see that each of these are points of inflection. So it just happens to be that all of these change concavity. So we start to the left of negative 0.49, concave down, and then to the right of that, it's concave up. Then at 0, we change to concave down, and then at 1.1, we change to concave up. So all three of those will be points of inflection on our graph. All right. Now that we have all that information, I went ahead and took those three critical values that we had before and plotted them. And so now my new viewing rectangle that I chose, so just a little bit of rationale behind why I chose it, was so I looked at my smallest x value here and my largest x value, and I knew I needed to at least be a little bit to the left and a little bit to right of those. And I decided to go from negative 4 to 3 just because I also remembered that I had this vertical asymptote at about negative 1.5, so I just went slightly to the left of that to also capture all that information. And then I chose negative 2 to 3 for my y values, just due to the fact of how our values of importance that we got here ranged. So I just went slightly outside of that, so it wasn't all squished together. So this pretty much looks like the exact same graph that we started with for the viewing rectangle. So it looks like we just got lucky this time.